problem solving exercises. And today we are going to see, so far we have seen Bernoulli's trial and geometric uh, progression, geometric series, um, and how it was used in probability questions. Now we are going to see another important topic, which is conditional probability. I know you might have studied this in your high school, but this is probably one of the most important topics. So let's just solve the first question. Question one says a customer will purchase a shirt with probability 0.5, and the customer will purchase pants with probability of 0.4, and will purchase both a shirt and a pant with probability 0.2. So what is the probability that the customer will purchase neither a shirt nor a pant? So let's break down all the probabilities that we have in our hand. Our objective here is to find the probability of not purchasing any clothes. So probability first is probability of customer buying a shirt. So probability of buying a shirt is 0.5, and probability of getting a pant is 0.4. And then we have probability that customer buys both, and that probability is 0.2. So let's find the probability that the customer will purchase neither a shirt nor a pant. What's the first step? First step is you will use the conditional probability formula, which is P, shirt and pant. So shirt union pant means shirt and pant. To get that, we use individual probability, probability of shirt plus probability of pant, minus probability of shirt and pant. Okay, so what is this? Probability of shirt, probability of pant, and this is probability of buying both shirt and pant. So this will give you the probability of union of two events. And if we plug the values, we get 0.5 plus 0.4 minus 0.2. The resulting answer is 0.7. Okay. Now, this is the probability that customer buys at least a shirt or a pant. So when I say probability of shirt union pant is getting either shirt or pant, or maybe both. So this 0.7 shows they either got shirt, they either got pants, or both. Now, if you want probability of getting neither, so probability of getting neither shirt nor pants, in that case, this will become 1 minus probability of getting either. And what is the probability of getting either? It's 1 minus 0.7. So your answer is going to be 0.3. I hope that makes sense. It's a very straightforward question. There is no complexity as such. Just using formulas to solve this problem. Okay. Now let's see question number 3. Let's try solving it here. Okay. Let A and B be two independent events of a random experiment. Then which of the following is or always true? Okay. So let's do this step by step. Let's say I think this is, oh, okay. I'm sorry. The second question was here. I did the first one and then directly moved to the third one. Let's do second as well. Let's not make this any complex. Okay. Question second. The answer here was 0.3. Suppose that we roll a pair of fair dice So each of the 36 possible outcomes is equally likely. Let A denote the event that the first die shows 5, B be the event such that the sum of the outcomes of rolling the pair of dice is 10, and C be the event such that the sum of the outcomes of rolling the pair of dice is 7. Then we have some options. Event A and event B are independent. Event A and event B are independent, are not independent. Event A or event C are independent, and event A and event C are not independent. Okay, so let's solve this step by step. Okay, event A. What is event A? So event A was uh, first die shows 5. That's event A. Then we have event B, which is sum is 10. Okay. Next up, we have event C. Sum is 7. So here is the thing. We roll a dice, and how many possibilities outcomes are there? So if we roll 2 dices, there are 36 possibilities. Okay. You know why? Because 2n, if you remember, so it's 2 times 2 times 2 times 2, 4, 5, and 6. 2, 4, 8. Oh, I'm sorry. No, 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 no. Hold on. So not this one. I'm getting confused with Bernoulli's. No. So the first die has 6 possibility, and then the 6 outcome, and the second has a 6. So you have in total 36 possibilities of events. So let's work through what each event means and how to test if they are independent. Events A. First die is 5. So you have first die as 5. All possible pairs where the first die is 5 is how many? So 1, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. What does it mean? The first die shows 5, that's fixed. The second die can show any number between 1 to 6. So how many possible outcomes are there? 1, 2, 3, 4, 5, 6. So 6 outcomes. And probability is 1 over 6. Okay. Now event B. Event B is list all pairs where sum equals 10. How is that possible? 4, 6 will give 10, 5, 5 will give 10, and 6, 4 will give 10. So how many possible outcomes can we achieve? So 3 over 36. Total sample space is 36. So you get the probability 112. Let's move to the side. Next up, we have event C, where sum is 7. So how many possible outcomes? 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So your final answer, how many possible outcomes? How many possible outcomes? We have 6. So 6 over 36 is going to be 1 over 6. Okay. Now, how do we check if events are independent? Okay. So two events, E and F, are independent. So let's say there's event E and event F. They are independent if probability of E and F, probability of E and F equals PE times PF. Okay. Now in A and B, first die is 5 and sum is 10. In event A is your sum is your first die shows 5, and event B is your sum is 10. So which outcomes have first die 5 and sum 10? Only 5 and 5. So this fits our agenda, which is to find if they're independent or not. So first die 5, second die 5, so sum is 10. In this case, here we go. This one. Uh, so if we check for their independence, okay, what's the probability of 5 over 5? That's 1 over 6. Okay, 1 over 6. And if you multiply that by second, which is event B, the probability is what? 1 over 12. So 1 over 6 times 1 over 12 will give 1 over 72. And this is not same as probability of A times probability of B. So this is not going to be independent. Okay. Second is pair A and C. Pair A and C is very independent. Why? Because pair A has probability 1 over 6, and event A has a probability of 1 over 6, and event C has a probability of 1 over 6 as well. So when you times both, you get 1 over 36, which is same as the original. Okay, and that's why this pair is independent. So we get only one answer. So event A and event B are not independent, which is, but let me select highlighter, are not independent. And event A and event C are independent. So second and third option are correct. Now let's move to question number 3. In question number 3, we have let A and B be two independent events of a random experiment. Then which of the following are always true? So you have question 3. Uh, let's recall the basic facts. Independence means, as I said, probability of A and B is probability of A times probability of B. Okay. Probability of both events happening is the probability of their individual probabilities. So probability of both events happening is the product of individual probability. Okay. Then you have union formula, PA union B. It's PA plus PB minus 2PAB. Not 2, sorry. Minus 2PAB. Okay. Now, if we insert independence into the union formula, so you have PAUB, then you get PA plus PB minus PA times PB. Why? Because it's independent. If it's independent, you can directly plug the formula number 1 in formula number 2. So that is only universally correct sometimes among the choices. Okay, let's check the options. So your first option is probability of A, B. Okay, so this option is going to be your correct. This is exactly what we derived in on the site. So you have probability of A union B, probability of A times probability of B, plus probability of B. Option number You know what? Okay. So I made some mistake here. Although not mistake, I failed to explain one thing. Let's go over these options to better understand. Step one. So we have two events which are independent, A and B. If the occurrence of one does not affect the probability of other, that means these two events are independent, which is the case. And if they are independent, we found this is the right formula. Okay. PA and B gives PA times PB. Now, if you see, let's first define something because we are getting confused here. When you have A union B, it means A or B or both. Okay. So probability of getting A or B or both. When you have A intersection B, this means A and B. So probability of having A and B. When you have B, C on top, that means it's a complement of B. So this means B does not happen. And finally, when you have P X X, oh shoot, X given Y, that means probability of X given Y has happened. And that's the conditional probability formula. Okay. So now we know it. General formula is already given here. This is the general formula. So let's first check option A. So option number one, it says PAUB. Let me remove this. This was wrong. Okay. So you have option one, PA union B, PA times PB plus PB. Now, if we test it, let's say PA is 0.5, PB is what? 0.4. Now, if this is since A and B are two independent events, that means PAB will be 0.5 times 0.4, which gives the final answer 0.2. Then actual probability of P union B, A union B, will be 0.5 plus 0.4 plus, oh, sorry, minus 0.2. The answer is 0.7. However, this should be the answer. But if we put these numbers in the first option, which is here, what are we getting? We are getting, okay, so our option was PA, probability of A, probability of B, plus probability of B. So if we do 0.5 times 0.4 plus 0.4 equals 0.2 plus 0.4, this gives 0.6. And this are not equal. That's why this option is false. Because if the answer was, okay, see the logic here. Logic is we have independent events, two independent events. Independent events means A union B is going to be directly, you can put the numbers to get the answer, which was 0.7. Sorry, 0.2. Okay. A intersection B. Why? Because two events are independent. Now, if they are independent, you can directly plug this number here to get the union answer as well. And our union answer turns out to be 0.7. However, their union, once we plug the numbers, does not give 0.7. It gives 0.6, and that's why this is a false answer. Likewise, we can go and do the second question. I'm sorry, not the second question, second option to check if that's true or not. I know it's lengthy, but these are basics, and it's important to learn the basics. So second option is, first, what is B probability of B and C? Second option has something probability of B complement C, right? This literally means 1 minus probability of B. That is going to be 0.6. That's it. Now, if you plug the numbers in this formula, so probability of A union B is going to be probability of A. Probability of A union B is 0.7. Okay, so if this has to be true, then the right hand side should also yield 0.7. Let's check. So the formula that they have given is probability of A times probability of B complement C. plus probability of B. Let's check out. If we do 0.5 times 0.6 plus 0.4, the answer we get is 0.7, which is equal to right-hand side and left-hand side. Okay, both are equal. That's why this is correct option. Option number 2 is correct. We are going to mark it. Now let's see option number 3. In the last option, option number 3, the formula given is PAUB plus PA plus PB. Outright, we can say this is false. It's not. This would only be true if A and B are mutually exclusive. Only true if A and B are mutually exclusive, which means they can't happen together. This is not true. If, let's say, rolling two dices are not mutually exclusive. And you also need to understand that independent events does not mean mutually exclusive as well. Okay? So, in fact, A and B are independent and have positive probability. They can happen together. So if you see the example again, your PA union B is 0.7. But if we plug the numbers here, you get PA plus PB. Your answer is 0.9, which these two are not same. That's why this is not independent. This is a false answer. Now let's check the last option that we have. Our last option is probability. Okay. Probability of A union B given A already happened. That is probability B. So this is a conditional probability of both A and B happening, given that A has already happened. Okay, so since A and B are independent, you can say probability of A union B is probability of A times probability of B. This turns out to be probability of A times probability of B. Okay. Now, but so see, if A and B are independent, we know that this is true. Okay, PA times PB. Probability of A times probability of B will give you the intersection. Now it's very simple. This formula, the conditional formula, is what? Probability of A intersection B, given that probability of A already happened, is probability of B. What is this? This is going to be probability of A union B. Okay. And I'm sorry. This is equal to just saying probability of A times probability of B over probability of A, because this is conditional probability. So this and this gets canceled, and your final answer is equal to PB. So I hope this makes sense. This is a formula. If you don't know, you can remember. This helps in conditional probability, this type of equation. So again, I hope this makes sense. This is also true, and that's why you are getting the answer as correct. This is correct, by the way. Next up, we have question number 4. Let's make some room. So we have the probability that a student registered for IITM online degree program will pass the qualifier exam is 0.6. Find the probability that out of 10,000 registered students, 7,000 will pass the qualifier exam. If you see the question, you will remember that we have come back to our binomial thing, right? So question number 4. So 10,000 students are there who have registered. So these are independent, identical, and independent trial. Now, each trial has 2 outcomes: pass or fail. Question is also asking that, pass or fail. 7,000 have passed. What is your K? Now, your K or the outcome that we desire for exactly 7,000. The keyword here is exactly. When things are exact, you use binomial. When things are vague or endless or infinite, then you use geometric formula. So I think you now know the binomial formula. This is your n. Then if you put the equation, you get 10,700 factorial, and then you get 0.6 because the probability of passing is 0.6 to the power of 7,000. For 7,000, we want to get the answer. 0.4 is not passing. 10,000 minus 7,000. This is going to be our answer. Now let's check the options. What's the option that we are getting? And it turns out that the third option is correct. No, I'm sorry, not the third one, the fourth one. This is your correct option. Okay, let's move to the next question, 5 and 6. First up, we have question number 5. Now, assume that the probability of a defective computer component is 0.05. Components are randomly selected for being tested. Assume that the testing is 100% accurate. Find the probability that the first effect is observed when the sixth component is tested. This is the same question that we got prior in the geometric series. Okay, the defective component. So the problem is, it's a classic example of geometric distribution. So this concept helps us find the probability that the very first success, in this case finding a defect, happens on a specific event, which is sixth. So what's the success? Finding a defect. Finding a defect. Probability of the defect is 0.05. Okay, that's what we know. Now, second is failure. What's your failure? Failure is probability of no defects. That is going to be 0.95. Now, think through the sequence. So the question asks for the probability that the sixth component is the first one that is defective, which means the first one is fine, the second one is fine, the third one is fine, the fourth one is fine, the fifth one is fine, and finally in the sixth one, you get 0.05, a defect. Now, if you do the if you now you have to combine the probability to get the total, but you have to remember: are you going to add or multiply? If you remember from my previous video, you know then that the keyword here is to check if the key thing here is to check if you're getting the keyword or and. So to get the first effect as the sixth item, you have to see that the first item is all right, no defects, and here's the keyword and. The second is also correct. The third is also correct, and fourth one and fifth one and sixth one. So because it's and, you are going to multiply to the power of 5 times 0.05. This will give you the answer, your correct option. So correct option, I think, is already given here. They're not asking the final answer. It's just this one. So I hope this makes sense. You can also use the formula of geometric distribution, which is basically, okay, hold on. It's basically pk 1 minus p, k minus 1 times p. Same thing. But I think you should use logic. It's very simple. Okay, now let's move ahead to our next question. If Arushi and Ansh play a game of chess, Arushi wins with probability 0.5 and Ansh wins with probability 0.4. And the game ends in a draw with probability 0.1, independent of all other games. They agreed to play a match consisting of 5 games. Find the probability that Arushi wins 4-1. Win gives 1 point to winner, and draw gives 0.5 points for both. So it's a chess problem. Okay. So this problem involves a fixed number of games. Question number 6, fixed games. And how many games were there? 5. And we need to find the probability of a specific set of outcomes. So this is a multinomial probability problem. So how many matches are there? 5. Score is Arushi wins 4-1. Arushi is 4-1. That's what we have to find. What is a scoring rule? Win 1, and if there's a draw, you get 0.5 both. How can Arushi get 4 points in 5 games and Ansh get 1 point? So if Arushi, she needs to win 4 games. So that will give 4 times 1, which is 4 points. Ansh must win 1 game. 1 times 1 gives 1 point. Okay? Ansh has to win 1 game, Arushi must win 4 games. And there has to be no draw. Because if Arushi wins any less than 4 games, she's not going to win. So 4 wins for Arushi, 1 win for Ansh, and 0 draw. That makes 5 games. And this works out. Now you have to find the probability. Probability of Arushi winning is 0.5. Probability of Ansh winning is 0.4. Probability of draw is 0.1. So this problem has 2 parts. Part A, the probability of one specific sequence here. First, let's just calculate the probability of one way this could happen. For example, what's the probability that Arushi wins the first 4 games and Ansh wins the last game? That is 0.5 to the power of 4, okay, times 0.4. This gives you the answer as 0.025. That's one. Now, but this is not your final answer because you don't know which way this will turn out to be. Okay? Why? Let me give you an example. This is only one way of solving a. Yeah, so this is 0.3, this is 0.08, and when you do the total probability, 0.08 plus 0.3, and this gives you the final answer at 0.38. Okay, so answer here is 0.38. Next up, we have, I hope this makes sense. It's just a law of total probability. This is, again, a formula, very basic from the your high school course, which is law of total probability. So you have 2 groups. You add the individual probabilities of those 2 groups. Okay. And then we have law of total probability. Oh, I'm sorry, question number 8. Question 8. Question 8 says, suppose you are playing a game of cards with your friends. Your friend is supposed to give you 13 cards one by one. With a well-shuffled pack of 52 cards, what is the probability that you are dealt a perfect hand, which is 13 of one suit? So a standard deck has 52 cards divided into 4 suits: hearts, diamonds, clubs, and spades, with 13 cards in each suit. So a perfect hand means 13 cards you receive are from the same suit. Okay, so 13 hearts, for example. Your friend deals 13 cards and from a 52 card deck, and we assume that the deck is well shuffled. So total number of ways this can happen. So your n is 52. Case 13, it's given. It's pretty straightforward. You do a 52 combination of 13. Is how many 13 cards you choose out of a pack of 52. So 52 factorial, 13 factorial, 52 minus 13 factorial. This is the formula. Now, number of favorable outcomes. A perfect hand means all 13 cards are from one suit. Since there are 4 suits, and each has exactly 13 cards, there's only one way to choose all of 13 cards from a specific suit. But there are 4 suits, so there are 4 possible perfect hands. So how many number of favorable outcomes? Number of outcomes are only 4. So probability is going to be 4 over total possible outcomes, which is 52, over 13 factorial was 52 minus 13 factorial. This is going to be our final option. So what's the option that we have? Okay, well, if you solve this, will go up and 4 will come down. So only third or fourth option can be correct. And in this case, if you solve, you get the final answer as 12 factorial, 39, and 51 factorial. This is your right answer. Oh, okay. You had this as well. 12 because, it got divided by 4. Yeah, this is very basic question. Nothing too complex here. So that's why I'm not pondering over it much. Well, let's see the next question, which is question number 9. So a person has bought a bed from an online furniture store. The seller delivers the disassembled bed parts along with some screws to assemble it. The probability of a screw being defective is 0.1, independent of all other screws. To compensate for the manufacturing error, the seller sends 2 extra screws in the package, where the bed needs exactly 8 screws to assemble. What is the probability that the buyer will be able to assemble the bed? Which means he's not going to require an extra 2 extra screws. So restating, the bed needs exactly 8 screws. 8 screws are required. 2 are extra. Each screw is defective with probability 0.1. Probability of defective is 0.1. Okay. What is the probability that the buyer can assemble? So the buyer can assemble the bed if at least 8 out of 10 screws are non-defective. So we want 8 out of 10 screws non-defective. There is no compromise. Let X be the number of non-defective screws among the 10. Each screw is non-defective. The probability of non-defective is what? 0.9. We can use binomial here. So why do we need it? So what's the logic here? Logic here is we need at least 8 screws. At least 8. As I said, this is a keyword, at least, which means we need exactly 8 screws, or exactly 9 screws, or exactly 10 screws to assemble. Okay, so we want him to screw the bed only when he has 8 screws, 9 screws, or 10 screws, which he has. If any less than 8 screws are defective, he's not going to assemble the bed. So these are the 3 cases. So probability of having 8 screws as non-defective will be 10 to 10 combination 8. 0.9 is the success of not having non-defective screws. We want them for 8 times 0.1, 2, which is 10 minus 2. I hope that makes. I think you are familiar with this now. Your probability is 0.9. Probability of having 9 screws non-defective, which is 10 combination 9, 0.9, 9, 0.1, 1. 0.38 probability that 9 screws are non-defective. Then probability of 10. You have 10, 10, combination 10, 9, 10, 0.1, and 0. So you have 0.348 as non-defective. So to assemble the screws, you need exactly 8 screws, or exactly 9 screws, or exactly 10 screws. That's why you are, because the keyword here is or, that's why you are going to add all these probabilities, 3.48 plus 3.387. Your final answer is going to be 0.929. Okay, that's your answer. Nothing too complex. Finally, we are going to solve the final leg of this exercise, which is problem number 10. So in a pizza shop, 40% of the customers order medium size pizza, 50% order small size pizza, 10% order large size pizza. Of those ordering medium size pizza, 2/3 also ask to add extra toppings. Of those ordering small size pizza, 1/5 also asked to add extra toppings, and of those ordering large size pizza, 4/5 also asked to add extra toppings. Given the customer asked to add extra toppings, find the conditional probability that customer ordered a medium. They are just making it more complex. Let's break down. 40% of them order medium. Okay. 50% ordered small. 10% ordered large. Okay. Yeah. Now of medium, now specific for medium, 2/3 ask for toppings, extra toppings. Small ordered 2/3 for medium. 1/5 asks for extra toppings. Large 4/5 asks for extra toppings. Now we are given that the customer asked for extra toppings. Customer asked for the extra toppings. That's given. What is the probability that they ordered a medium pizza? So probability of finding medium pizza that they asked for extra toppings, which is going to be, now you're going to use Bayes' rule, Bayes' probability rule. Probability of finding medium times probability of finding extra given medium over probability of extra. This is Bayes' principle. So your answer is going to be very straight. If you compute the numerator, you get this formula can also be written as probability of medium times probability of extra given medium. So your answer here is going to be 0.4 times 2/3. This is going to be 40 over 100 times 2 over 3, 4 over 15. Okay. So probability of having extra, if you do the total probability of asking extra, is what? 0.4 times 2 over 3 plus 0.5 times 1 over 5 plus 0.10 times 4 over 5. This is the probability of getting extra. So now in the medium part, and why did we achieve this answer? What is this actually? This is for medium. This is for small, and this one is for large. So if you add them as fractions, if you add all of these as fractions, 4 over 15 plus 1 over 10 plus 2 over 25, this will give you the answer at 67 over 150. Okay, so probability of extra is 67 over 150. Now probability of medium given extra is going to be 4 over 15 times 150 over 67. Your final answer is going to be 40 over 67, and this is 0.57597, or 40 over 67. This is your answer right here. Number 6 was, oh sorry, not this. This wasn't number 6. This was number 9. Number 9 was 0.929. That was our answer in number 9, 0.929. I hope this makes sense. I think we are done with the exercise. We'll have one more exercise, which will be this lengthy and time taking. Then we will finally move to other topics.